Hello everyone, my name is Isabelle Kuhlmann. I work at the University of Koblenz-Landau in Germany, and today I will present a work that I did with Matthias Thimm called An Algorithm for the Contention Inconsistency Measure using Reductions to Answer Set Programming. When working with real-world data, we cannot really avoid getting some conflicting information. So for example, if we require knowledge from different experts, or more generally, information from different sources, we are bound to get some pieces of information that contradict each other. As an example, you can think of weather forecasts from different weather sources. So how do we deal with inconsistent information? Well, there are different ways to look at this problem, and the field of inconsistency measurement provides a quantitative and analytical perspective on this. There are different methods of measuring inconsistency, but here we focus on the contention inconsistency measure. Furthermore, I'd like to point out that these types of problems are complexity-wise quite hard. So for example, the problem of deciding an upper bound with respect to the contention inconsistency measure, so not even the value itself, but only an upper bound, is NP-complete. Thus, it's quite crucial to find practically feasible algorithms to deal with these kinds of problems. So what we did is we created an algorithm for the contention inconsistency measure by using reductions to answer set programming. And we also implemented this approach and evaluated it against an existing implementation. Now I will go over some preliminaries. Mainly, I will describe the contention inconsistency measure and the basics of answer set programming. First, what exactly is an inconsistency measure anyway? Well, an inconsistency measure is simply a function that maps a knowledge base to a positive real value. The intuition behind this is that we assign large values to very inconsistent knowledge bases and rather small values to less inconsistent knowledge bases. Or in other words, the more severe an inconsistency, the larger the inconsistency value. The value 0 indicates the absence of inconsistency. So if a knowledge base gets the value 0, it means that it's consistent. To understand the contention inconsistency value, let's first take a look at Priest's three-valued logic. As the name indicates, this logic involves three truth values. So in addition to the two classical truth values, true and false, we also have a third value that indicates paradoxical or both true and false. And we will denote this as B. And here you can also see the truth tables for this. I will not go into this in detail. I will come back to this in a little bit. And just like in classical logic, in three-valued logic, we also have the notion of interpretations and models. So an interpretation is simply a function that assigns one of the three truth values to each atom in a knowledge base. We can also divide the domain of an interpretation into two groups. The first one includes those atoms that are assigned a classical truth value, so true or false, and we call this binary base. And the second one includes those atoms that are assigned the truth value B, and we call this the conflict base. Now, a model in three-valued logic is an interpretation where each formula in a knowledge base is assigned either true or both. In this way, we can also define the set of all possible models. Finally, we can define the contention inconsistency measure. Essentially, this measure simply describes the smallest possible conflict base. The intuition behind this is that we're looking for the minimum number of atoms that need to be assigned B in order to make the knowledge base consistent. So let's take a look at an example here. This knowledge base given here, K1, contains three formulas, A and B, not A or B, and not B and not C. In classical propositional logic, this knowledge base is clearly inconsistent because if you look at the first and the third formula, A and B and not B and not C, there is clearly a conflict. In three-valued logic, however, we can find a model for this knowledge base. If we assign, for example, true to A, false to C, and both to B, we actually have a model. I mean, we can also find models where, for example, each of these atoms gets assigned B, but since we're looking for the smallest one, well, this is it. So the smallest possible conflict base contains one atom, B, and consequently, the contention inconsistency value for this example knowledge base is 1. As the title of our paper already reveals, we used answer set programming for our approach. So what is answer set programming? Well, answer set programming, or short ASP, is the declarative programming paradigm, and it's targeted at difficult search problems. What this means is that instead of modeling instructions on how to solve a problem, we model a representation of the problem itself. More specifically, we present our problem in a logical format And the models of this representation then describe the solution of the original problem. And these models are called answer sets. So what does an answer set program look like? Well, we can also call these programs extended logic programs, because as opposed to regular Prolog-like logic program, in answer set programming we have two kinds of negation. So there's the classical logical negation, and there's also the negation as failure, or the default negation. Well, and then we can define rules of this form here. So we have head of the rule and the body of the rule. And yeah, A1 and to AN and B1 to BM as well as H are literals. Furthermore, a rule with an empty body is called a fact, and a rule with an empty head is called a constraint. Also, there's the notion of cardinality constraint. The intuition behind this is that we have a lower bound L and an upper bound U, and the cardinality constraint is satisfied if at least L and at most U of the literals inside the set are included in the answer set. These types of cardinality constraints can be used as both heads and body elements of rules. Alright, next I will describe how we utilize the answer set programming to measure contention inconsistency. Now the idea is the following. We have knowledge base and we also have a value U. And now what we do is we encode the problem of whether this given value U is an upper bound for the contention inconsistency value with respect to the given knowledge base. And then what we can do is we can use binary search to localize the actual inconsistency value. Now let me elaborate this a little bit. First of all, we know the maximum value because it corresponds to the signature size of our knowledge base. And well, let's just call this n for now. So in binary search, we can set the initial value of our search to n over 2. Now, if the answer set program returns an answer set, it means that n over 2 is actually a valid upper bound for the contention inconsistency value, and we can try a lower value next. If it doesn't return an answer set, we have to try a higher value next. And this way we will eventually find the true contention inconsistency value. So how do we encode the problem of deciding whether a value is actually an upper bound for the contention measure in ASP? Well, we start by introducing some new propositional atoms for the answer set program. And essentially for each atom X, we create three new ASP atoms, and we call them EXT, EXB, and EXF. So we have one atom for each truth value. We also create such atoms for formulas and for subformulas. Now let's start setting up some rules for the answer set program. Now first of all, we want to check whether a given upper bound is actually valid. We incorporate this into our answer set program by setting up a cardinality rule. The lower bound of the cardinality rule is 0 because, well, it could be that knowledge base is consistent, so this is our minimum value. And the upper bound is defined by the current value in the binary search. The atoms inside the cardinality rule are those that refer to the evaluation of each original atom to B. Besides, we need to ensure that each atom only gets one evaluation, one distinct evaluation. So an atom shouldn't be, for instance, true and both at the same time. So we encode it like this. For example, if X is evaluated to true, it cannot be evaluated to B and it cannot be evaluated to F. And it works the same way for the other two truth values. Also, we need to ensure that each formula evaluates to either true or both. And we do this by setting up these integrity constraints for each formula. What's still missing from our answer set program are encodings for the different logical connectors. To be precise, we created encodings for AND, OR, and NOT. Now let's recall the truth values for Priest's three-valued logic. Now, for example, regarding the conjunction operation, we can see that there's only one case where the formula actually evaluates to true. And that is where both X and Y are also true. And here you can see the corresponding ASP rule. So this rule contains three different ASP atoms. This one represents the conjunction of X and Y being evaluated to true. This one represents X being evaluated to true. And this one represents Y being evaluated to true. So what this rule means is that if the conjunction of X and Y is true, then X must be true and Y must be true. Now let's look at the other two truth values. If we take a look at the truth table, you can see that we get false whenever either Y or X is false. So essentially whenever X is false, it means that X and Y is also false, and it's the same for Y. So we encode this in two different rules. So X and Y is false if Y is false, and X and Y is false if X is false. Now we only have the truth value both left, and well, the conjunction of x and y evaluates to both if it doesn't evaluate to false and if it doesn't evaluate to true. Now the rules for disjunction and negation are basically constructed in the same way. Now let's go over a quick example. Here we have the same inconsistent knowledge base K1 that we already saw earlier. And let's just say we choose 2 as the upper bound. Now as the first step, we set up the cardinality constraint. The lower bound is of course 0, and the upper bound is, as I just mentioned, 2. The atoms in the cardinality rule are those that represent each atom in K1, so A, B, and C, being evaluated to both. Next, we need to ensure that each atom only gets one distinct truth value. So for example, A can only be true if it's not both and not false, and well, it's the same for B and C, and also for the other two truth values. So A can only be both if it's not true and not false, and so forth. Then we need to add integrity constraints for all formulas. So A and B cannot be evaluated to false, not A or B cannot be evaluated to false, and well, not B and not C can also not be evaluated to false. And finally, we have to encode 3 formulas. I don't really want to go into detail here, but you simply have to apply the scheme that I presented 2 slides ago. So for example, for the first one, for A and B, well, it's exactly the same that I showed you. Well, A and B can only be true if A is true and B is true, A and B can only be false if, well, either A is false or B is false, and so on. As I mentioned in the beginning, we also implemented this approach and performed an evaluation. What we did is we compared our algorithm to an existing, to the best of our knowledge, the only existing implementation. This implementation, which is, by the way, provided by the Tweety project, follows a brute force approach. So in the first step, the given knowledge base is converted to CNF and checked for consistency. And, well, if the knowledge base is consistent, 0 is returned. Otherwise, for each proposition X, we remove each clause containing X and check for consistency again. And this is essentially equivalent to setting X to B. Now, if one of these new knowledge bases is actually consistent, we return the value 1. Otherwise, we have to repeat this process with each pair of propositions. And, well, if one of the new knowledge bases is consistent, we return 2. Well, if it's not, and if we still didn't find a consistent knowledge base, then we have to look at each triple and so forth. Here you can see some results. We performed our evaluation on a dataset of 800 random knowledge bases that we compiled using the syntactic random sampler provided by the Tweety project. And then we measured the execution time, sorted the results, and plotted them. Also, we set a timeout to 60 seconds. You can see that the naive approach, here in blue, performed okay for some instances, but for others it did way worse, and actually for 53 different knowledge bases there was even a timeout. Now the ASP approach, on the other hand, stayed well under 10 seconds for all instances. Now to conclude, we introduced an algorithm for calculating the contention inconsistency measure by means of reductions to answer set programming, and we showed that it clearly outperforms the state-of-the-art. Regarding future work, well, we will definitely try to enhance our existing implementation, and we will extend the approach to other inconsistency measures. Regarding enhancements, one idea is to use first-order logic instead of proposition logic in the answer set rules. Alright, that's it. Thank you for your attention.